Hello everyone, welcome to my channel. I am Kinza Azab with registration number 21TE03. Today we will perform Lab 5 of Digital Signal Processing, and the main objectives of our lab are the representation of discrete time signals into frequency domain, resolution of spectrum, and computation of magnitude, phase, and power spectrum, and spectrum leaking and avoiding spectrum leaking. Starting with our task number 1. In our first task, we were asked to make our functions for calculating discrete time Fourier transform and its inverse using the formulas of Fourier transform. So this is a code. In this code, my DFT computes the discrete Fourier transform of the input signal x, and my IDFT-x computes the inverse discrete Fourier transform of the input spectrum x. Four test signals x1, x2, x3, and x4 are defined for demonstration purposes. These are arbitrary sequences of numbers representing discrete time signals. For each test signal, the custom DFT function myDFT is used to calculate discrete Fourier transform. Similarly, myIDFT is used to calculate the inverse discrete Fourier transform of each spectrum, resulting in reconstructed signals. MATLAB's built-in functions FFT and IFFT are used to calculate DFT and inverse discrete Fourier transform of each test signal, resulting in x1 built-in, x2 built-in, x3 built-in, x4 built-in, etc. And the code then displays the result for each test signal, comparing the outputs of custom and built-in functions for both discrete Fourier transform and inverse discrete Fourier transform. And for each signal, the output is shown here. For each signal, custom DFT result is displayed, built-in DFT result is displayed, and custom inverse discrete Fourier transform result is displayed. Also, built-in discrete inverse discrete Fourier transform result is displayed. The purpose of this code appears to be to demonstrate the correctness and equivalence of custom DFT and inverse DFT implementations with MATLAB's built-in functions by comparing their outputs for different test signals. This is commonly done to verify the correctness of custom signals processing algorithms. In our next task, task was calculate discrete Fourier transform for the signals and observe the change in frequency spectrum. These were the signals which we were given in the question, and we have to find the discrete Fourier transform of these signals and also plot their magnitude spectrums. So firstly, let's observe this output. The magnitude spectrum of all the signals are shown here. This is the magnitude spectrum of x1, x2, x3, and likewise. So in this code, several signals x1 to x11 are defined with different lengths, and some signals have zeros added to them to make their length powers of 2 for more efficient FFT computation. The discrete Fourier transform of each signal is computed using MATLAB's FFT function, resulting in x1 to x11. The magnitude spectrum of each signal is plotted using STEM command. For signals x1 to x3, each signal spectrum is plotted in one figure with multiple subplots showing the magnitude spectrum of each signal with different lengths. For signal x4 to x9, each signal spectrum is plotted in separate figures here. Each subplot or figure is labeled appropriately with titles indicating the signal's name and then the length of the signal. Axis labels indicate the frequency index scale and the magnitude of the corresponding frequency component. So this code helps visualize how the magnitude spectrum of a signal changes with different signals length. It's important for understanding the frequency contents of signals and for analyzing their spectral characteristics. Moving towards our next task. In this task, we were given an arbitrary signal. Firstly, we will observe its output. This is the output of the signal. Okay, let me explain the code. A signal x is defined as 1, 2, 3, and 4. The discrete Fourier transform of the signal x is calculated using the FFT function, resulting in x. The real part of the frequency spectrum x real is extracted using the real function, and the imaginary part of the frequency spectrum is extracted using the imaginary function. And the magnitude of the frequency spectrum x magnitude is computed using the ABS function. The phase angle of the frequency spectrum x angle is computed using the A tan 2D function, which calculates the 4-quadrant inverse tangent in degrees given the real and imaginary parts. The inverse discrete Fourier transform of the frequency spectrum x is calculated using the IFFT function, resulting in the reconstructed signal XS. The code essentially demonstrates how to compute and analyze the discrete Fourier transform of a signal. It calculates the real and imaginary parts, magnitude, and phase of the frequency spectrum, and then reconstructs the original signal from its discrete Fourier transform. This is a common procedure in signal processing and spectral analysis. This is the output. This is original signal. This is discrete Fourier transform of the signal. This is real part of frequency spectrum. This is imaginary part. This is the magnitude of frequency spectrum, phase angle of frequency spectrum, and this is the reconstructed signal or the inverse discrete time Fourier transform of the frequency spectrum. Moving towards our last task. In this task, we were asked to calculate the discrete Fourier transform and plot magnitude spectrum, phase spectrum, and power spectrum for the signals in the task 2, and also observe the effects of zero padding. Okay. Signals x1 to x11 were given in the question. Several signals x1 to x3 are defined with different lengths n. The discrete Fourier transform of each signal is calculated using the FFT function, resulting in x1 to x3. The frequency x is defined for each signal to represent the normalized frequency values. This is calculated by the formula. This one. 3 subplots are created in a figure for each signal. Okay, let me show you its output. These are the magnitude spectrums for each signal. These are the phase spectrums for the signal, and these are the power spectrums. 3 subplots are created in a figure for each signal representing the magnitude spectrum, phase spectrum, and power spectrum. Okay, each subplot displays the phase angle against the normalized frequency, and 3 subplots are created to represent power spectrum. Each subplot or figure is appropriately labeled with titles indicating the spectrum type and the signal name. Axis labels indicate the normalized frequency and corresponding spectrum value, magnitude, phase, or power. This code provides a comprehensive visualization of the frequency domain characteristics of each signal, including its magnitude, phase, or power spectra. This information is crucial for understanding the frequency content and distribution of energy in various signals. Thank you.